All right, so we're going to do a special case of conservation of mass. I'm sorry, a special case of conservation of momentum. With a rocket. Now, as we've said before, this is the second of the 3 hardest things we will do all year. The first one was change of reference frame. The second is this, and the third is angular momentum. Because nobody gets angular momentum. It'll be fine. Okay. So, there are some things that you have to remember and know. So, the first thing that you have to remember about a rocket is that the rocket itself loses mass at a rate of -r, where r is the rate of fuel consumption. So the way a rocket works, if you think about the space shuttle, is the space shuttle has 2 tanks of fuel that happen to be liquid oxygen and liquid hydrogen. It allows those 2 kinds of fuel to mix, and when they mix, what do you get when you mix oxygen and hydrogen? You get water, okay? And so they mix, they form a gas. The gas gets pushed out one way, and to conserve momentum, the rocket has to go in the opposite direction. That's the way a rocket works. You just have to find the right mix of fuel. So that fuel, whatever it is going to be burned, fused, however you want to put it, at a certain rate. Every second, I'm going to be consuming, or the rocket is going to be consuming a certain amount of fuel and converting it to a gas, but then that gas leaves the rocket. So whatever rate at which the fuel is being used, that's also the rate that the rocket is losing mass, because the fuel is converted into a gas that becomes exhaust. Okay, you with me? Okay. And the second thing that you have to keep in mind and remember is that we need our system to be the rocket and the exhaust. Because if I let my system be both of those things, then we have a closed, because I'm not really losing any mass, isolated system. And if I have a closed, isolated system, what can I say about it? Momentum is going to be conserved. Okay, so you have to keep those things in mind, because things are going to get a little funky. Okay. All right, everybody got what they need? I can wait a second. Okay, we good? All right. So the first thing that we're going to try to find is the acceleration of the rocket. We're going to try to find the acceleration of the rocket, and we're going to try to find the velocity of the rocket, an expression for the velocity of the rocket. Because those are things you'd want to know. So since I'm going to be talking about momentum, I'm going to need an initial state and a final state. So my initial situation is I have a rocket that has some mass m that's moving that way. Okay. Sometime dt later, so I don't necessarily have a collision, but we've also talked about conserving momentum before and after an event of some kind. And in this case, my event is just that an amount of time dt has elapsed. Okay? So sometime later, I have my final state. And in my final state, I've got my rocket, and I have exhaust. Now, the mass of my exhaust is going to be equal to the mass that my rocket lost, right? That makes sense? Yes. Okay. And we're going to say that the rocket has ejected a mass absolute value dm. So the rocket ejected a mass that. Okay. And if the rocket has lost some mass and we're conserving momentum, what's going to have to change? Its velocity. So we're going to assume that it's still moving this way because reality tells us that the rocket doesn't turn around and go the other way. Okay. And it's now going to be moving at some velocity v plus dv. Now the mass gets tricky. In all of the problems that we've done, in calculus and here, we always think of dm or dx or d whatever it is as being positive. But here, the rocket is losing mass. So that means that dm is less than 0. dm is negative. Yes, so. Because once again, it's not, remember, okay, first of all, remember that dm is a change in mass. Okay. Second of all, as the omniscient and omnipotent narrator, this is going to make the math work out easier. And that's really why we do it, is it's a construct that makes the math make more sense later. Okay, so this means that m plus dm is less than m. If dm is negative, then this is like really subtracting something. So when I do m plus dm, what I end up with is something less than what I started with. And that also means that negative dm is greater than 0, which means that I don't really have negative mass. I just have a negative change in mass. And if I take that negative of the negative change of mass, I end up with a positive amount of mass. I told you this is the second hard thing we're going to do this year. The second of the 3 hardest things we're going to do this year. And this is part of it, is you got to free your mind. So if we go back up here, the mass of our exhaust is going to be negative dm in the final state. And the mass of our rocket is going to be m plus dm. But you can see that if I add the mass of the exhaust and the mass of the rocket together, I'm still just going to end up with m. Okay? It'll be okay. Trust me. And of course, our exhaust is going to have a velocity that I'm going to call u. Please note that I did not give it a direction. Although, which direction do you think it's going to be going? The whole rocket's moving this way. Mm-hmm. 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 No, it's definitely not going to stay still. It's actually going to move this way at a much smaller velocity in that direction. But my total momentum still has to go that way. Because the whole system is already moving that way. We are looking right now from the Earth. If you were sitting on the rocket, it would be moving that way, but you're not. So you can probably guess there's going to be a change of reference frame coming. All right. So, of course, if I've gone to all the trouble of calling this a special case of conservation of momentum and writing an initial state and a final state, I'm going to conserve the momentum, right? So I'm going to say that the momentum in my initial state is going to be equal to the total momentum in my final state. So initially, I've just got the mass of the rocket and its velocity. Please be careful and mindful of your V's and U's and make sure you make them differently. And then I'm going to have the mass of my exhaust times the speed of my exhaust plus the new mass of my rocket times the new speed of my rocket. Now, everything's moving along the same direction. Okay, and I can just set an axis in that direction. So I'm going to drop my arrows. So it's going to be mv is going to be negative dm times u plus m plus dm times v plus dv. And this, like I said, is the momentum of the exhaust. And this is the momentum of the rocket. And now we're going to throw in a change of reference frame. I actually put like a little smiley face in my notes because it's a poop eating grin smiley face. Change your reference frame. And this is for those of you who are going to grow up and be rocket engineers sometime. Okay. So, V plus dV is the velocity of the rocket with respect to the ground, the earth, whatever you want to call it. I don't want to use an E because I'm going to have exhaust in a minute. And U is the velocity of the exhaust with respect to the ground. And then I'm going to introduce a new variable, which is VREL, and that's going to be the velocity of the rocket with respect to, bless you, the exhaust. All right, you with me? So if we go back to that lettering system that we used when we did reference frames, this would be the velocity of the rocket with respect to the ground. This would be the velocity of the exhaust with respect to the ground. And this would be the velocity of the rocket with respect to the exhaust. Okay. Hang on a minute. The bottom line is I need VREL. I'm going to need VREL for something I'm going to do later. So omniscient narrator again saying this is what we're going to do. So, okay, so give me a statement to write down. Let's do it this way first. So what is it? No, let's do it with these first. Plus negative. That works too. And then I don't have to have a negative sign. The velocity of the rocket with respect to the ground is equal to the velocity of the rocket with respect to the exhaust plus the velocity of the exhaust with respect to the ground. You were doing more steps than I was all at once. We're going to get there. Okay. but let's make sure everybody understands this step first. I love it when you work ahead, but we got to make sure that everybody's there. Okay, so everybody gets where this comes from. Okay, so if we put everything in, then the velocity of the rocket with the ground, with respect to the ground, is v plus dv. The velocity of the rocket with respect to the exhaust is vrel, and the velocity of the exhaust with respect to the ground is u. Right? Based on the way we defined things. So actually what I'm going to do is I'm going to solve for u and substitute in, and then I'm going to introduce vrel into my conservation of momentum equation. So u is going to be v plus dv minus vrel. Okay. All right. Okay. So I'll just write it again. So here was my momentum equation. You can just draw a line. You don't have to write it again if you don't want to. Okay, but now I'm going to substitute in for u. So I'm going to have mv is going to be negative dm times v plus dv minus vrel plus m plus dm times v plus dv. And then what do you think we're going to do? Well, I'm at least going to get rid of all my parentheses and see what happens. Okay, so I've got mv. I'm going to have negative vdm minus dm dv plus vrel dm. Plus mv plus mdv plus vdm plus dm dv. I can cancel out all kinds of cool stuff. Let's make sure everybody's got this. Priya, got it all written down? Okay. Yep, that's what everybody was saying. Let's let everybody write it down before I start marking it up. Well, I don't know. Sari and no, Sari and Elisa were both still writing. Okay. So my MVs cancel. Thank goodness my DM DVs cancel, because you guys can't even do regular integrals yet, let alone double integrals. I love you, but we're not there yet. Yep. But remember that there's a 0 on the left-hand side. Okay, a lot of people forget that. Okay, so that's going to give me not vrel dm plus mdv. And in calculus, we like to have the DMs, we like to have the D whatevers, the differentials, we can use that word because we all know what it means. We like to have the differentials on different sides of the equation. So I'm going to write this as negative VREL dm is equal to MdV. Now, what did I tell you I was looking for? Acceleration. You got an idea how I can get acceleration out of this puppy? What is it, Lisa? Right, so if I divide this whole thing by dt. What?
I don't know how I feel about this.
Because remember, I'm separating my before and after, my initial and final by this time dt. And then things get a little weird again. So what's this? dv dt. That's going to give me a acceleration. What's that going to give me? Negative dm dt. No, not quite. Which is what? The rate at which, yes, which is what? Which is what? Then look at your notes. The rate of fuel consumption, which is what? Everything I write down is important, and you should write down everything I write down. R was the first thing. So R is negative dm dt. That's what rate of fuel consumption means, is how the mass changes with respect to time. So what we get is R VREL is equal to MA. No. And so if my goal was to solve for A will be R VREL over M. And the reason that we went through, well, one of the reasons that we went through a lot of this is that engineers talk about the thrust of a rocket, which is equal to RV-rel. So if you're going to grow up and be a rocket scientist, you're going to have to know what that is. Okay, we good? We got it? All right. So now let's find the velocity. V of the rocket. So we're going to back up a couple steps to negative VREL dm is equal to mdv. Okay, just a couple lines. And in a couple of weeks, you'll look at that and you will just need to integrate it. You're just going to look at that and go, I can't just leave it there. I need to do that. Just like sometimes you just have to factor a polynomial and cancel stuff out because you just can't help yourself. Laugh at me all you want, but you will be there, Sarah. Okay. So I need to rewrite this a little bit because I need to get all my m's over with my dm's. So I end up with negative v rel dm over m is going to be equal to dv. And then, like I said, you're not going to be able to help yourself, and you're going to want to integrate. But I'm going to integrate between some initial velocity and some final velocity. And some initial mass and some final mass. Okay. And so, what's the antiderivative of dv going to be? No. No. Yes. What's the antiderivative of dx? X, because there's really that 1 hiding in there, which we really think of as like v to the 0. Okay, so it's going to be v evaluated between some v initial and v final. The tricky one, what's the antiderivative of 1 over m? LF. So it's going to be the natural log of m evaluated between some m initial and m final. And then we're just going to substitute in here. So I've got negative v rel natural log of m final minus natural log of m initial, and that's going to be v final minus v initial. We're going to solve for that change. So we're just going to worry about the left-hand side. We'll leave v final minus v initial the way it is. Okay. So what can I do with those natural logs? Nope. I can combine them. Yep. And then, yeah, I think I want to go there. What about that negative sign? So that means I can flip my fraction, right? Flip this fraction because that negative sign in front, I can make it the exponent of whatever I'm taking the log of. Just like 2 natural log x is the natural log of x squared. But if I make it to the -1, that means I take the reciprocal of my fraction. Okay? We good? We got it? All right, then let's do the 2 problems that we have. So page 254, number 96. These are rocket problems.
So this is all like in preparation.
Yeah. We had to learn what we were doing. We had to learn what the problem was. Somebody read it for us, please. Okay. So, here's my solar system. Here's my rocket. And they tell me that the velocity of the rocket with respect to the ground, aka the solar system, is 6.0 times 10 to the 3rd meters per second. Now, it can be important to make sure you get the right labels on everything, on all the numbers that are given in the problem. So what kind of numbers do we have other than this one? Some of them are easy. Come on, there's 3 numbers there. Shout out a number. Ah, you picked the hardest one, Sari. Okay. VREL, if you look back in your notes, is the velocity of the rocket with respect to the exhaust. And what do they actually give you? What is that 3.0 times 10 to the 3rd meters per second? What is that measured? Right. So in order to make it VREL, what do I have to change? The sign. Okay. Because it's the number they give you is the velocity of the exhaust with respect to the rocket, but we need VREL to be the velocity of the rocket with respect to the exhaust. Okay? Somebody give me another number here. So that, and the units are? So that's what the mass is. That's what big M is. The mass of the rocket at any moment. And then what's the other thing that we have? Right, so we know the acceleration is 2 meters per second squared. Okay. So now what does part A ask us to find? The thrust, which is T. And what's my expression for T? RV rel. Now I have the V rel, but do I have R yet? No. But what's RV rel equal to? MA. Do I have MA? Okay, so I can find the thrust another way using MA. 4 times 10 to the 4th kilograms times 2 meters per second squared. And what's that going to give me? Which I think is actually in Newton, but I've never seen thrust written that way. I'm pretty sure it's in Newton, but I don't think it's a unit that we use for thrust. Okay. Everybody with me? All right, so what does part B ask? And what variable is that? R. How am I going to find R? Yeah. T over V rel. So that's going to give me 8 times 10 to the 4th kilograms meters per second squared divided by -3 times 10 to the 3rd meters per second. Which gives us what? It's a 2 sig figs. Is she right? Okay. All right. Let's see if we can do the other problem. So let's do page 255, number 113. If somebody would read it for us, please. Yep. Okay. So that's a hopper cart. Usually they're filled with coal, but I'm assuming you could put grain in one too. They go past my house. Okay. And it's moving at a constant velocity of 3.2 meters per second. Now, why do I need to add a force to keep this moving at constant velocity? Because the mass is increasing, right? The grain is dropping down and adding to the cart. If you were sliding by on your skateboard and I dropped a bowling ball that you caught, what would happen to you? The friction comes in later, but what has changed about you? What has changed about what? Mass. You got to think about the momentum. If I add mass to something, the speed has to go down. If I assume that momentum is conserved, which I can if I have no friction, which is kind of weird because you have to have friction to make the wheels turn, but that's beside the point. Right. So as I add, well, it did. I was waiting for you guys to get there. Okay, so if I add mass, but I want to keep going at the same speed, I have to have a push. I have to have something external that's going to keep it going, because the natural thing would be to conserve momentum. If I add some mass to it, it's going to slow down. Okay, I think the bell's going to ring. So I think we're going to stop here because we're at the beginning of this problem.